Okay, in this video we're going to look at a more formal version of hypothesis test. Okay, so this is building off of the last video. Okay, so we left off asking ourselves, it's natural to question the point at which the sample result transitions from being not statistically significant to being statistically significant. Okay, so again, with this more formal set for hypothesis test, okay, that's what we're going to get into now. Okay, so what a hypothesis test is it uses sample statistics to examine a claim about the value of a population parameter, whether it's mu, p, or a sigma. Every test will have two hypotheses. The null hypothesis, okay, which is called h sub 0, or h naught, and the alternative hypothesis, which is h sub a, okay, or ha, okay, for alternative. The null hypothesis will always have a statement of equality. Okay, so in the example that we had in the previous video was the machine dispensing 20 ounces. So the statement of equality was that mu equals 20. The alternative hypothesis, HA, will always contain the statement of inequality, okay, meaning a less than, greater than, or a not equal to sign. Now in practice, generally, whatever a researcher is trying to support is the alternative hypothesis, HA. Okay, so the way we view a hypothesis test is as follows. We assume the null hypothesis is true. Okay, like in our soda example, we assume that the soda machine was dispensing 20 ounces. So we assume that HO is true, okay, meaning that mu equals 20 is true. And then what we do is we collect evidence, so we take a sample, and determine whether the data is inconsistent with HO. When the sample is inconsistent with HO, then we have evidence against HO. However, if we do not have this evidence against HO, it does not mean that HO is true. Okay, it just means that we don't have enough evidence against HO. Okay, so a good way to think about this is thinking of courtrooms. We assume the defendant is not guilty. The prosecutor presents evidence. If there is enough evidence against this assumption, then we reject that he is not guilty, or she. Okay, it's not only guys committing crimes, right? Okay, so we reject that he is not guilty if there's enough evidence against that assumption. If there is not enough evidence presented, then we declare the defendant not guilty. Okay, so again, we start by assuming that the defendant is not guilty. We present evidence. If there's enough evidence against that assumption, so if there's enough evidence against not guilty, then we reject that he is not guilty, which means we're going to say he's guilty. If there's not enough evidence presented, then we declare the defendant not guilty. Okay, so if the evidence says that we can't say that he is guilty, then we would say he's not guilty. Okay, so number 4, write the null and alternative hypotheses when we assume the machine dispensed 20 ounces on average. Okay, so this we already mentioned. The null hypothesis contains a statement of equality, so mu equals 20. Okay, that was the null. Now notice I'm not saying that HO equals 20. Okay, it's a very common mistake students make is that HO equals 20. That makes no sense. Your null hypothesis is that the population parameter, in this case mu, equals 20. The alternative to that was that we were concerned that it was dispensing less than 20 ounces, so the alternative was that mu was less than 20 ounces. Okay, but it could also have been worded that maybe if you're the company, you were concerned that the machine was dispensing more than 20 ounces, well then you could say that mu is greater than 20 ounces as the alternative. It just depends how the question is worded and how you're looking at it. Okay, you could also say maybe we're concerned that the mean is not 20 ounces, which means it could be less than 20 ounces or greater than 20 ounces. Then you would have mu not equal to 20 for the alternative. And we'll get into that in a few minutes. Okay, so again, more formally with the hypothesis test here, we have something called a test statistic. Okay, the test statistic is the z-score that corresponds to our sample, and the p-value is the probability associated with that test statistic. So what is a test statistic and the p-value when our sample mean is 19.97? Okay, now this went back to the previous video. Okay, so I hope you're watching these in order. Okay, and what we found in our previous video was that when we took 50 bottles, the sample mean was 19.97. We found a z-score to be negative 1.06. So that is what we're going to refer to as our test statistic. The probability associated with that z-score, so the probability that x bar was less than 19.97 was the same as the probability that z is less than negative 1.06. And that probability, when you look it up in your z table, is 0.1446. Okay, so for that example that we did before, the test statistic was z equals negative 1.06, and the p-value was 0.1446. Okay, and again, that's from looking it up on our z-axis. Negative 1.06 for the z-score, the area to its left, 0.1446. Now, what's important, or what's we're building on here, is what is that p-value telling us? The p-value is the probability of getting a result as extreme or more extreme as our sample produced from a population whose mean is our assumed value. Now remember, our assumed value here was that mu equals 20. Small p-values contradict our null hypothesis and support the alternative hypothesis. Okay, so what happened on this one was that we said that a z-score of negative 1.06 was not a very extreme value because it's only 1.06 standard deviations below the mean. Now remember, our original distribution for that had a mean of 20 because that was our assumed value for mu, and 19.97 was just below 19.972. Okay, so that p-value of 0.1446, so the area to the left of this x bar value of 19.97 was only 0.1446 area to its left, okay, which is not a very small probability, okay, meaning that it's not unusual to get that value. Okay, small p-values contradict our null hypothesis and support the alternative. Okay, so the other one that we did in that last video was we got a 19.90 for the sample mean. And remember, 19.90 had a z-score of negative 3.53, which was way over here. So the probability to be to the left of 19.90 or to the left of a z-score of negative 3.53 ended up being 0.0001. So that's your p-value, 0.0001, which is a very small p-value, which means, again, in the context here, that we were far away from the 20. Okay, so 19.90 is far enough below the 20, okay, way over here, okay, to say that that's an unusual result to get if the mean really was 20. You would expect the mean to be less than 20 in order to get a 19.9 as your sample mean. Okay, so that's how you look at p-values and what they mean. Now, there is some individual subjectivity involved in determining whether a value is unusual, okay, or not. However, typical values for these significance levels, indicated by the Greek letter alpha, okay, so this symbol here is alpha, are 0.05 and 0.01. Okay, 0.10 is also fairly common. Okay, we are saying that if p is less than alpha, so for p-value is less than alpha, then our sample produced an unusual result, and our assumption of the null hypothesis was faulty. Now, what this alpha actually represents is the probability of rejecting our null hypothesis when the null hypothesis was actually true. You want that to be a very small probability. Okay, so this 0.05 and 0.01, in the courtroom example, it'd be rejecting that the defendant is not guilty when he really is not guilty. Okay, you don't want to send an innocent person to jail. Okay, so you want the probability of that happening to be very small. Okay, so that's what the alpha represents, is the probability of rejecting the null hypothesis when the null hypothesis is really true. Okay, in practice, we should always check the following simple conditions are met, although maybe they're not realistic. Okay, first thing you take a simple random sample from the population of interest. And again, all that means is that each sample has the same probability of being chosen, okay, or the same chance as being chosen. Okay, so if you take a sample size 50, those 50 values have to have an equal chance of being chosen, okay, to be included in your sample. Okay, the random variable follows a normal distribution. Okay, so we want our x distribution to be normal. We do not know mu, but we do know sigma. Okay, so right now everything we're doing hinges on the fact that we know what sigma is, which again is not going to be very realistic, and in future chapters we'll take care of that. Okay, so moving along to the next page. So here's a formal hypothesis test. Okay, so if all that stuff with the p-values and all that didn't make any sense, hopefully when we do the example here, it'll make more sense. So suppose a sample of 50 bottles resulted in a sample mean of 20.05 ounces. Perform a hypothesis test if we claim that the mean amount of soda dispensed was more than 20 ounces on average. Use a significance level of alpha equals 0.05. Okay, so first thing we're going to do for an hypothesis test is state the hypotheses. We have a null hypothesis and alternative hypotheses. So remember, your null hypotheses, HO, always has a statement of equality. Well, when we look at what we're doing a hypothesis test on, it's the mean amount of soda dispensed being more than 20 ounces. So the mean amount is mu. Because the null hypothesis always says equals to, the null hypothesis is that mu equals 20. The alternative hypotheses, when you read the question, they're saying the mean amount was more than 20, so more than would be greater than 20. So your alternative hypothesis is that mu is greater than 20, and that is what they're trying to claim. Okay, is that the mean amount dispensed was greater than 20. Okay, so then what we do is, once we have our hypotheses, we collect the evidence. Well, we calculate our test statistic. We collected our evidence of 50 bottles. We found their sample mean to be 20.05. We're using the same standard deviation as before, the 0.2, and the mean of, again, our mu is 20. So our z test statistic, x bar minus mu sub x bar, divided by sigma of x bar. So when we substitute our values in, z equals 20.05, which was our sample mean. That's the evidence we collected. Minus mu sub x bar. Well, notice that's the same thing as what mu is, because in theory, we're assuming that the center of our x bar distribution is the same thing as mu, 20. Okay, that's the assumption that we made, was that mu equals 20. Divided by sigma over square root of n, okay, which was sigma sub x bar. Okay, do those calculations, and you end up with a z-score of 1.77. Okay, so now what we look at is we want to ask ourselves, is that z-score an unusual value? So is it unusual to get a sample mean of 20.05 if the mean of the population really was 20? Okay, so is that unusual? Well, is 1.77 an unusual value? Well, that's where we need to now look at alpha being 0.05. Okay, so how we do that, you draw your distribution. Okay, and hopefully we can see this okay. Our distribution, we're assuming that 20 is in the center. If we went one standard deviation above the mean, this value right here is 20.0283. Okay, that's adding 0.2 over the square root of 50 once. So one standard deviation above the mean is 20.0283. The second standard deviation above the mean is 20.0587. Our value of 20.05 is just before that. Okay, so I know it's a little jumbled here. If I draw that a little bit bigger on this one. Okay, I should have made that bigger on the original. Again, 20 was right in the center. 20.0283. That has a z-score of 1. and then .0587 that had a z-score of 2. The value that we have right about here has a z-score of 1.77, and the x bar value was 20.05. Okay. So our x bar value, 20.05, is the same place as a z-score of 1.77. And what we're looking at, or what we're concerned with, is what p-value, or what is the probability that we are above that value. Well, when we look up the probability that z is greater than 1.77, that's when we have to do 1 minus the probability to its left of 1.77. So when we look up 1.77 in the table, okay, so positive 1.77, okay, that gives us, is it 0.9616? Okay, so when we do 1 minus 0.9616, again, that's the area out here, 0.9616. So 1 minus that will give us the area to the right of 1.77, or the x bar value of 20.05. So that area is 0.0384. Okay, so this area out here, from here to the right, is 0.0384. Okay, and that is the p-value. Okay, so what that represents is the probability of getting a sample mean as extreme or more extreme than 20.05 in this distribution. Okay, so getting a value that is more than 20.05 for x bar has a probability of 0.0384. Okay, about a 3.84% chance. Now, is that significant or not? Now we go back and look at alpha. Well, alpha is 0.05. So 0.05, again, we're looking at being greater than 20, right? So we're looking at 0.05 being out to the right here. Well, if you look at 0.0384 compared to our alpha value of 0.05, 0.05 is going to have to go more area this way. Okay, so that 0.05 is going to include more area there than the 0.0384 did. So 0.05 area from here to its right, okay, that's alpha. Oops, that was a terrible alpha. That's alpha. Okay, so what just happened here is that our test statistic of 1.77, which corresponded to an x bar value 20.05, is more unusual than we were willing to accept based on our alpha value. We only wanted a 5% chance, or a 0.05 probability, of rejecting HO when HO was really true. Well, we're saying that the probability of getting a value of 1.77, a z-score of 1.77 or more, an x bar value of 20.05 or higher, has a small probability of 0.0384. Okay, so that is far enough away from 20 to reject the null hypothesis. Okay, so that 20.05 sample mean, even though it's only 0.05 away from 20, in terms of the variation in our distribution and our sample size, that value is far enough away to say that 20 was not okay to assume for the population mean. Okay, so what is the decision that we make? Well, 0.0384 is less than 0.05. Okay, p is less than alpha. So our p-value is less than what alpha was. So that means we're going to reject the null hypothesis. Now again, you don't have to memorize, okay, p is less than alpha, so we reject the null hypothesis. Okay, look at it the way I explained it here. 0.0384 is a smaller probability than 0.05. So that means that this value, whether you're looking at the x bar or the z, was far enough away from the center of 20 or a z-score of 0. Okay, they were far enough away from the center to say that that center was a faulty assumption, that 20 is a faulty assumption for the population mean.